Today we'll talk about the logging technique. So while we drill, we can gather some information. What rock type is there, the formation type, and whether there is a hydrocarbon or not, so whether there is oil or not, or if it's gassy or not. Right? So today we'll talk about how we get some information during the drilling. It's called the formation evaluation. So that's the chapter 3.2. So let me read this paragraph. So geological engineering information can be gained when cores are recovered, but coring is so expensive. It's in the coring device, but you can often use it, but it costs money. So measuring the geophysical properties with the aid of wireline logs formerly after drilling section of the well and before setting the case is very useful, and it's called measurement wire drilling or logging wire drilling. So what they do is that if you're drilling the hole with this string, and this is bit, right? And then in this section, you install some sensors and measure the physical values using these sensors. It's called the logging, and you can measure the formation resistivity and sonic velocity and density here and the radioactivity. So measure data interpreted to determine the rheology and porosity of penetrated formation and type and quality of the fluid, whether it contains the oil or gas and the water within the pores. So it looks like this here. It's called a sand, right? Cylindrical sand, and you can install some like electrode and like piezo crystals or the pressure meters, etc., etc. And this is the this wing-like mechanical equipment needs to measure the borehole diameter. So it has a spring and has some gauges. So as you drilling goes down, you can like slide and it touches the wall of the borehole. So it measures the diameter. It's called a gauge. So there are numerous types of logging methods: electric log, and radioactive log, and the sonic acoustic log, porosity, nuclear magnetic resonance log, so NMR, dielectric, heat meter, and borehole. So we're gonna briefly glance through it, whether what are they and what's the role of them. So the first is the spontaneous potential, or we say self-potential or SP log. And this is the oldest type of geophysical log in use. SP logs, you can see from this figure, right? So you have just one electrode, and the other, you have a voltmeter, which measures the voltage, the potential, and the other electrode is the ground. So between here and here, you just measure the potential difference, the electrical potential difference. And it can only be used in open, uncased hole filled with conducted mud. So this doesn't have any active source. You don't need any like power or the battery. It just measures the self potential or the natural potential in the ground. So it's just passive measurement. And because you have an electrode in the sand, the cylindrical rod, so the surrounding fluid should be conductive. If you have like oil filled in water, filling this borehole, then the electrical current doesn't flow. So the filling fluid should be conductive. And salinity difference between drilling mud and the formation water causes the SP response. And this SP log has four main uses: detection of permeable bed, so it can detect the differentiate the shale and the permeable, impermeable and permeable bed. And the determination of the RW. Here, we're going to use the R as the resistivity. So water, the formation water resistivity, an indication of the shaleness of a formation, and the correlation to the porosity of the hydrocarbon content. Okay. Let's just get one by one. So, how it works. So, what is formation water? Formation water. You said it's a pore water. Okay? So, this is pore water, or some people call it connate water. Connate water, formation water, pore water are the same. So that's the interstitial water in the rock matrix. And the chloride, so let's imagine that this is the original condition. You have a membrane wall at the center, and this is more concentrated electrolyte. So sodium and chloride is there, and this is more dilute electrolyte. So you can imagine that there will be a movement of the ions from one side to the other, right? So always you have a diffusion from higher concentration to lower concentration. So here, the sodium and chloride ion will move, right? But fortunately or unfortunately, chloride ion have a higher mobility than the sodium ion. So Cl diffuse faster into the mud filtrated zone, and a current flow from the mud filtrated zone into the formation water. So what it says is that if you have a chloride ion going from here to here, because the electron is moving this direction, the current will flow the other direction, right? And it's called the liquid junction effect. And if we apply this concept to the borehole case, here you have a mud. So this is the borehole filled with mud, right? Drilling fluid. And normally the mud is mud salinity. Here, okay. Formation water is the more concentrated solution than the muddy water. So mud salinity is less than the formation water. Formation water salinity. So you have more concentrated sodium and chloride ions here, right? And this chloride ion will diffuse to the mud filled this borehole, right? From here to here. So here the higher salinity and the low salinity. So as you have the chloride ion movement, the current will flow from here to here, right? So then you have an electrode, voltmeter. So this will, you have current flowing, to this direction, right? Through the ground. And this potential, electric potential, is called the liquid junction potential. And that's because of the concentration difference between the formation water and the mud filtrate, or the drilling mud. You can notice that there's always some invaded zone because this is permeable bed. Permeable bed is one. The shale, you don't have much the invaded zone of the muddy water, but because it's permeable, as you drill, it can penetrate a little bit, and you have some region with the invaded zone. And the second mechanism of the self potential is the membrane potential. If you have a shale formation, the shale have very unique characteristic. Here is made of clay, right? And clay has what? Clay has charge, and it's negatively charged. Normally, the plate surfaces are negatively charged. So it attracts the cation, and you can transfer the cation from one side to the other side. So when you have a clay, whenever you have a clay, it repels the anion because its electrical double layer has the negative charge, and it attracts the cation. So it works as a selective ion barrier. So it transfers the sodium ion only, and it repels the chloride ion. So that's going to be the other way. So in the case of the diffusion, you have a chloride ion moving faster, but in this case, sodium ion will move much faster. So shell are more permeable to sodium ion than the chloride ion. Then potential exists at the junction between non-invasive. So here, from the original condition, Cornell water is more saline than this mud filtrate, and you have a shell which is very low permeability, but it can transfer the sodium ion. So sodium ion will move to here. So because the plus charge is moving this direction, you have a current flowing this direction to the same direction. So net current flow will occur this direction. So since the sodium ion penetrates the shale bed through from the saline formation water to the less saline mud column, a potential is created, which is known as the membrane potential, right? EM. So if we can summarize it, here. Okay. Let me add one more time. So here. So if you have an electrode here, voltmeter, because the current is flowing this direction, right? So it's going to be the different opposite response to the first one. So here you have a current going down, right? But going down from voltmeter to the downhole. And in this case, current is going up from the downhole to the voltmeter. So you have an opposite response when you have a shale, when you meet the shale and the sandstone, the permeable bed. So from that, we can differentiate the whether it's permeable or shale. So here you have a several response. When the resistivity of the mud fluid, so this is the resistivity. And the MF mud fluid or the mud filtrate. And W, the subscript W means that the formation water. So when the resistivity of the mud filtrate is larger than the resistivity of formation water, the SP deflects to the left. So that's the case when you meet the sandstone, right? And when MF is less than the resistivity of the formation water, SP deflects to the right. That's the positive or reverse SP potential. So when these two values are similar and there's no SP deflection. So you can see that this is the baseline. Here, this is the baseline. And normally the baseline is from the shale formation. And when you meet some permeable bed, then you have reflection like this. So here you have some permeable bed and the other permeable bed to the left and another reflection to the left here. So we found 3 permeable sandstone formation in this SP log. And in shallow, so let's say here, let's look at the sand here. It deflects to the left, right? So it's a reverse and it's a normal SP potential. And this is the case when the muddy fluid resistivity is larger than the water resistivity. So A, it should be larger than the formation water resistivity. Then, what about in the case C? You have a reverse, right? The reverse SP potential. So it's going to the right direction and it deflects positively. So this means that the water resistivity is larger than the mud filtrate resistivity. Actually, in shallow sand, it's common to find the fresh water and more saline water as depth increases. So as you go deep, the salinity will increase. Naturally. So this is the common case in most cases. What about in sand B? So you have a deflection. This normal SP response, but its magnitude is less than the sand C. So we can expect the salinity of this water is a little bit less than this one. It may be more diluted than the water in the deeper region. So still it's resistivity of the mud filtrate is less than the water. But if we compare the water resistivity A, B, C, right, then the C will be the largest one. This is the shallow one, right? And the A is the deepest one, and that's the smallest one. Okay, let me check again. So, what's the relation between the salinity and electrical resistivity? Checking the concept. We took the geophysics class. So, as salinity increases, electrical resistivity increases or decreases?
Decrease.
Why?
Ions.
You have more ion to carry the electrons, huh? Okay, good. So, in the formation C and in formation A, you can see the difference. And from this kind of a deflection, whether it's a positive deflection or negative deflection, you can find out which location is the permeable bed, the sand, sandstone, or the carbonate.
이게 왼쪽으로 이렇게 누르면 RNF가 크다는 거 아닌가요?
그렇죠.
그러면 스탠드 B에서 왼쪽으로 이렇게 된 거 아니에요? 그러면
그러네. I'm sorry, it's typo. It should be this direction. Nice. Good comment. So B and A, because it has negative deflection, resistivity of the mud fluid should be dilute, more dilute than the formation water. Other comment? Okay, good. So this is typical response. You have an impermeable shell. So the shell will give you the baseline. So here, this is the baseline SP. And from the baseline SP, you see only the how much it deviates from the baseline. So when you have a sand and fresh water, it will give you the positive reflection, and salt water give you the the negative reflection. Brackish water and impermeable formation, it's not very different, right? Each other, shale and impermeable formation. And the salty sand, salt water, and clean sand, you have a negative deflection. So this is the one way to just finding out the lithology and the formation. So I think just another summary. You guys can read it through. Okay. So in shallow depths, again, you have a reverse SP, right? In the shallow depths, positive SP, right? And in the normal SP is the deep depths when the salinity of the mud is less than the salinity of the formation water. So. Just a review that we just covered in the last slides. We move on. Okay, so the amount of, so then we can quantify the electrical potential from the difference between the mud filtrate resistivity and the formation water resistivity. So this is the main equation, and there are a lot of correction chart about the RMF and the RW and the K, but just looking at this equation, and this is the SP charge, and K is the constant which corrects the bore temperature, and the RMF is the electrical resistivity of the mud filtrate, RW is the electrical resistivity of formation water. So SP log is mainly, we use it to delineate the permeable zones, and hence it aids the source identification and well-to-well correlation, and to calculate the RW, the resistivity of the formation water. But it cannot be run in cased hole. So if you have a steel casing, then this flow of the current will be disturbed, right? And it can be blocked. So it should be used in the open hole. And is ineffective when the R of the mud is approximately equal to the RW, which is the case for the offshore drilling. So in the onshore, we use the tap water, like surface water, to make the mud fluid. So when you prepare the drilling fluid, you have a bentonite, dry bentonite powder, and you mix it with water, right? And where do you get the water? If you're at onshore, like somewhere in Texas, you go to the stream or the reservoir or lake, you just pump out the water. So that's gonna be very fresh water. But if you do it in in Gulf of Mexico or like Norwegian offshore side, the Ullum Basin, you're gonna use the seawater, which is available around the platform. Right? So you're gonna mix the dry bentonite with the seawater, and then you use it as a drilling fluid. So because you're mixing it with seawater, the salinity is very high. So then there might be no difference between the mud fluid resistivity and the formation water. So then SP doesn't give you very good information in those cases. So ineffective when the R mud is equal to the R formation water. Question. So there are some lecture notes, very great lecture notes from 2 different classes. So I'll send you the PDF copy of these 2 lecture notes. You can read it through. So the second is the resistivity logs. And resistor is the charge flow is driven by applied voltage and the resisted by the medium as predicted by Ohm's law. So Ohm's law is like what? V equals IR, right? And here the R is the resistance. Resistance is affected by the size of the material. For example, if you're measuring the electrical resistance of this table, if you measure resistance from here to here, resistance will be less than the case when you measure it from here to here. Right? So if the length is large, so the R is the kind of a mass. You can think of the mass, and the resistivity is the density. So you have to normalize to the normalize it to the size of the material. So here R is defined as the resistivity times D, the diameter. Oh no, this is the distance, I think. And the A is the area. Thank you. So in general, I think as a proportionality. So R will proportional to the distance. So from here to here, distance. Because as you measure the resistance at short distance, you have a small resistance. But if you increase the distance, you will have or the length, the resistance will go up. And what about the area? Area is related to the available area for electron to flow. So if you have a larger area, it's like the water flow. If pipe is larger, then the water flow will be faster, right? So it's more, the current can flow more easily if you have a larger diameter. So the resistance will be inversely proportional to the area, right? And also R is proportional to the material property, so electrical resistance, resistivity. So if you just multiply everything, combine everything, then R will become T over A. Which becomes the same equation that you have in here. And what is sigma? Sigma is the reciprocal of electrical resistivity. So sigma is called the electrical conductivity. And it's the same with 1 over rho. What is the unit of electrical resistivity? So here R is ohm and A is what? Length square, right? So square meter. And the D is the distance, so it is just length, meter. So ohm meter is the unit for the resistivity. Very straightforward. So, can we move on? Okay. So these are the electrical conductivity of selected material. Let's see, what do we recognize here? Calcite 10 to the negative 14 cellin per meter. So cellin per meter is 1 over ohm meter, right? So just the 1 over resistivity. So 10 to the negative 14 means that it doesn't conduct, right? The electron or the electrical current cannot flow through this calcite. And diamond has some kaolinite itself. Dry kaolinite is very low conductivity, and magnetite, that's 10 to the 4, so it has some electrical conductivity. And quartz, 10 to the minus 15, so it's just non-conductive. And oil, pure water, fresh water, seawater, you can see the difference, right? So oil is basically it's non-conductive, 10 to the negative 11. And fresh water, 10 to the negative 3. And like deionized water or the distilled water that we use for the experiment normally has a 10 to the negative 6, okay, in that order. And the seawater is 4. And aluminum, like the other like metal material, is 10 to the 7. So this is very conductive. So three main ways of measuring the electrical resistivity of formation is normal log, lateral log, and induction log. And it looks like this. And I think this A is the most common way to measure the electrical resistivity, normal log. And so the explanation of each logging method. The electrical potential and the flow of the current is set up between an electrode on the sand and electrode at the surface. So let's go back to this slide. And these black electrodes are the current electrode. So it flows the current. You have a battery that generates the current. So then you will have a current going somewhere like this direction, and from the X and Z electrode, you measure the potential in between. So here you measure the potential difference between the X and Z. So electrical resistivity that you're measuring represents the formation between this X and Z location, right? So this is just generating the current, and you're measuring the potential difference between these two locations. And lateral log and induction log, I think this is the special equipment when you have a special cases. So high resistivity. Okay. Resistivity of the sandstone or carbonate and resistivity of the shale is made of clay. Which one will be bigger? Sandstone resistivity and the shale resistivity. 철암. Because the shale has more clays, so as you have more clays, clay is more conductive than the sand particle, so this will be larger. Huh? So this is the case. For example, let's look at here, high resistivity and permeable formation full of oil, gas, and fresh water. You have high resistivity. This is because of the oil, right? And all the fresh water. And so up to this point, you had the shale. Up to this point, you have a permeable bed, like sandstone. And again, shale. And permeable formation, if the permeable formation is saturated with salt water and you don't have much like signal in the electrical resistivity log. And when you have a just tight formation, and here this is the tight carbonate and sandstone here, and the continuous shale will just give you this kind of a baseline result. So by looking at the SP and the electrical resistivity log together, you can qualitatively identify the formation in the bottom side of this formation. Especially they are looking at the permeable formation, right? Because it's easier to produce the hydrocarbon from the permeable formation. Okay. Okay, one more thing. And here, in the normal log, you have a X and Z electrode, and you can control the distance between X and Z. So if you increase the distance between X and Z, you're measuring the potential in the far field from the wall. And if you have an electrode very close together, X and Z, maybe like T here, then you're measuring the electrical resistivity in the very near field from the borehole, right? So if you measure the shallow, so this is called a shallow measurement, and this is called a deep measurement. And if you measure the shallow measurement, and that's more affected by this mud filtrate. So you have a flushed zone with the mud bearing sand, and you have a mud cake here. But if you increase the spacing, and when you measure the electrical potential, then the current can flow to the deeper region. So you're measuring the formation resistivity, it's the original resistivity of the formation. And people use it, the shallow and deep logging together to see the difference. And because it gives the more rich information. So then, in shallow measurement, it will be more affected by this mud resistivity, right? Because the water will filtrate to the near field of the borehole, and deep measurement will reflect the in situ formation. So from that, we can look at this kind of idealized example. So when the fresh mud, where the you have a fresh mud, and deep log is here. So mud filtrated area, shallow log will give you the higher resistivity because the R of the mud filtrate is higher than the formation resistivity. But the deep one will give you a little bit of less value, smaller value than the shallow log. So this is for the case when the mud filtrate resistivity is larger than the water resistivity. And in the other case, oppositely, if the salt mud is used, the formation water had less salinity than the mud. So the resistivity of the formation water is larger than the resistivity of the mud filtrate. And which one is the deep? Deep one will give you the higher resistivity, and the shallow will be more affected by this mud, so it has the lower resistivity. So from these two measurements, they can measure it at the same time actually while they're drilling. And from these two measurements, you have a more richer information. So then, if we combine the SP and the resistivity together, what can we know from this information? From the SP, so here was the tight shale, the tight limestone, tight formation, and you have a negative response, which is normal SP response. Then in this region, what do you have? You have, from here to here, you have permeable bed, which have a high permeability, right? And then when it ends, then we go back to the baseline value. So let's see. You have a permeable sandstone. You can identify the thickness of the permeable sandstone from the ST. And then what does resistivity tell you? You have deep log, dashed line, and a shallow log, a solid line. Dashed line is going this direction, and shallow is like that. Okay? So shallow is just more like flat, and dashed one, it has higher, and then it becomes the lower than the shallow log, and the shallow log represent here mud resistivity, right? So then this means that here you have very high resistivity fluid, and here you have a low resistivity fluid in the formation. So we can guess in this region you may have a oil or gas, which is non-conductive, and here you will have just the brine or the water, right? Formation water. 혹시 질문 여기까지. Okay, so we can identify this is kind of a candidate for the potential station for the hydrocarbon. And then we need to know the how much is in there, right? So then we can use some other equations to correlate the electrical resistivity to the hydrocarbon saturation of the quantity. That's called the Archie's law that we're going to cover in soon. Quantification of hydrocarbon saturation from the electrical resistivity is actually reverse, because the water is more conductive than the oil. So we find out first the water saturation, and then we just subtract the water saturation from one, then we'll get the hydrocarbon or the gas saturation. So, so this is just the again the review about the electrical resistance and the resistivity. So this is the resistivity here, right? R or the rho. And so then sand particles are electrically non-conductive, and pore water are much more conductive than the solid. So if you assume the brine filled porous medium, let's say so this is the sand, and here is the water, and here will be just the air because it's dry, and water saturation. By the way, what's the definition of the water saturation? Christine, do you know?
Probably the amount of space that's filled with water instead of air.
And out of what space?
Well, the space that is not filled with sand.
Oh, that's good. Right. So fluid saturation is the volume occupied by this fluid divided by the pore space. So if the pore, which is the space except the sand is occupying, so if the pore space is filled by water 100%, then it's 100% water saturation. If it's filled by air or the gas, which if it's dry, then it's 0% water saturation. Okay. From here to here, maybe we may have some intermediate stage with some water, right? Maybe some water here. Right? So as we go from left side to the right, so as we filling the water in the soil, then what happens to the electrical resistivity? So when you think about the path for electrons to flow, then here this is all sand. Sand is non-conductive. You don't have any path for the electrons, right? So and here you have all waters. Through the water, the charge can flow. And here, when you have the partially saturated case, so this is the case between 0 to 100%, you have a less path, but still you have a more path than the dry case. So as you increase the water saturation, electrical resistivity, okay, let me decrease, or the R decreases. Very basic physics, and we can think of the porosity too. And these are all filled with brine, so this is all filled with saline water. And 0% means that you don't have any pore, right? It's all filled with solid. And 100% is what? It's just the water, right? Just all water. And in between, maybe like 50%, this is solid and water. Again, as you go right side, so as the porosity increase, resistivity will decrease. And you can replace the air with oil. It doesn't change anything, right? Oil and air, they are not electrically conductive. So from this basic principle, Arch developed his equation. So the formation resistivity factor is the resistivity of the rock, 100% saturated with pore water, and divided by the water resistivity. So this reflects the skeletal structure, right? So if the F increases, what does it mean? So F is like 2, then R0 is 2 times RW, right? So then resistivity of the rock itself is twice rather than the water, pore water, right? So if F increases, then resistivity of the rock increases. So then maybe the formation factor can be correlated to the porosity. Inversely, it can correlate to the porosity. So Arch made an equation. Here you can see that the porosity is inversely related to the formation factor. So formation factor decreases as the porosity increases. And the A is the constant. And if you write the full equation with the water saturation, then it becomes like this. So here, the this term is the same with the formation factor. We have to hurry up. We have only 10 minutes left. Okay. So in clean clay-free formation, water saturation can be calculated. And I think this is very straightforward. So from this governing equation, this is the main equation, Archie's law, and you can drive it through for the formation factor, and so the water saturation can be measured or estimated from this R0. R0 is the measure for the ocean to be 100% water saturated rock, and the RT is the one that we measure from the deep resistivity load. So this is an example here. So if you meet the water bearing zone, you can find out the R0, right? And the RW can be correlated, can be calculated from the SP, because the SP is defined as the K times the log RMF over the RW, if you remember this equation. Then we have the RW, R0, and RXO is from this here. And then the difference here can tell you about the water saturation. So from the logging, as you go deeper, you know which region is fully saturated dry and which region is the different, and which region have the value of the mud cave, so then you can compensate all the affecting parameters and you can extract the water saturation. So detail, you don't have to know all the details, but just be aware of the basic concept of the Archie's law and how they use it. Okay. I hope I can finish the radioactive laws by today. So there are three major types of the law that measures the radioactivity: gamma ray, neutron, and density. Gamma ray is, they measure the scintillation counters from the natural radioactivity. So you have to have a natural radioactivity from the formation. Then you just measure the scintillation counter. And in the geology formation, the potassium is the main source of the radioactivity. And that's found in elliptic clay. So illite have potassium ion, and that potassium ion can give you the radioactivity. And to a lesser extent, you can find it in feldspar, mica, and the other. Gamma ray log is important for identifying the lithology and shearness. Okay, and this alone cannot differentiate the radioactive mineral, but you can use it to differentiate the kaolinite from the mica, because the kaolinite is a non-radioactive, the mica is radioactive. And to analyze it more specifically, they use it. They analyze the wavelength spectrum. Then from that, you can find out the ratio between thorium and the potassium and the uranium. So this thorium and uranium and potassium are the parent elements giving and providing the radioactivity. So by measuring the radioactivity from these three elements, you can find out the mineralogy of the formation. And the neutron log is more common, and that measures the neutron, the number of the neutron particle when you shoot it with the some radioactive source. So, and this neutron log is the same as the densometer that we use for the pavement. So when we check the compaction or the dry density in the field, we bring some equipment, right? And that's the neutron densometer. It's the same principle. And neutron bombardment caused the rock to emit the gamma ray in proportion to their hydrogen content. And hydrogen occurs in all formation fluid, oil, gas, and water, but not in the mineral. So for example, the quartz or the calcium carbonate made of, like calcium carbonate is CaCO3, right? And the quartz is what? Silicon dioxide, so it doesn't have hydrogen. So the oil, the fluid have the hydrogen, like hydrocarbon and methane gas or the water. So response of the neutron log is essentially correlated with the porosity. It works well in clean reservoir, but not in shale. Why? Because shale has clay, and clay can have the hydroxyl ion, and the hydrogen bonding between water. So it always have some bonded water, and so the neutron log will give a higher apparent porosity in the dirty reservoir. So dirty reservoir means that you have a sandstone with some clay. Okay, so the hydrogen content of the oil and water is about equal. So you can look at this table here, and this table shows the hydrogen content of some common earth element. The water hydrogen density is about 0.67, brine 0.61, and N-octane 0.67, right? So this is oil, and this is gas, and this is water, right? And you can find out the water are pretty much the same in terms of the hydrogen content with the oil, but when you compare with the methane gas has much lower, right? Hydrogen density. So hydrogen content of the oil is higher comparing to the hydrogen gas. So when you measure the neutron log in the gassy formation, it will give you a very low porosity. And the good thing about the neutron log is that this can be run in cased hole because there is neutron penetrated steel casing. Okay, let me move on. And the last one is the density log. Density log measures the formation density by emitting gamma radiation from the tool and records the amount of gamma radiation reflected from the formation. And I think this is just a very basic equation, right? The bulk density is a function of the solid density and the fluid density and the porosity. And presence of the oil has little effect on porosity value, but gas lowers the density of rock, thus causes the load to give too high a porosity. So the neutron log, in the case of neutron log, if you meet the gas formation, then it will give you too low porosity, but if you use the density log, it will give you too high porosity. So if you combine these two logging information, you can also identify where the hydrogen gas is occurring. Let's look at this example. So here the gamma, this is the gamma ray log. It just gives you the different value for different lithology, right? So here and here and here, I think this is the shale, right? And this is the permeable bed. And again, shale. Yeah. So then, what is the neutron log? So dashed line, this one is the neutron log. So this is the porosity that's estimated by this Newton law. Oh, sorry, this is the density value. And the solid line is the density value estimated by the density log. So in the oil and water reservoir, if it's filled with oil or water, you can see that these are all, they stack together, right? Density log and Newton log. But when you have some other fluid like gas, then this will give you, these two will deviate each other, right? So you can see this is the density, high density for the Newton log, and low density for the density log. So this should be the gassy formation. In the density log, scattering is less. In the gassy formation, so density is low. And in the gassy formation, the hydrogen density is less, so the neutron LPU value is less. So LPU value is decreasing to this direction. What about in shale? In shale, it's reverse, right? So neutron log gives you low density, and this is what? The density log gives the high density. Why this gives you the low density? Neutron log measures the hydrogen, right? And if you have shale, then shale has clay, also it has the hydrogen. So this neutron log recognizes the shale as fluid because it contains also the hydrogen in the shale. Does it make sense? So it gives you the very low density.
위에가 이쪽으로 갈수록 더 하이트는 갈수록
이쪽으로 갈수록 하이. 그치? 그러니까 하이, 오케이. Neutron LPU value increases, then it means that you have more fluid. So if you have more fluid, because the fluid is lighter than the solid, so you have the less density. Density here is less, and it increases to here. And neutron value is more hydrogen and less hydrogen. So they are correlated inversely. And they calibrate to be able to convert it to the density value. Okay. Other question? I think we need to stop here. Yeah. Okay. We'll stop here. And from next class, we'll talk about the other method in the logging, and then we'll talk about the staging method. 궁금한 거 어렵나요? 이게 헷갈리죠? Can be very confusing.
저거 이해가 안 되는데 유치원 교류가 하면 커피 비즈니스가 나는 좀 요즘에 숫자가 훨씬
네. 지금 뭐냐면 LPU 밸류가 높으면 하이드로전이 많다는 거예요. 그래서 LPU 밸류가 0이면 그냥 라진 거야. 그래서 2.7 g/cubic 나와요. LPU가 0이면 퀄츠에서는 그냥 2.65 this is the solid density. 이게 스페이스 그래피티랑 똑같습니다. 그러니까 LPU value 0 means that you don't have any fluid. High LPU value means that you have fluid. So here you have fluid, you have no fluid. Okay? 그래서 in gassy formation, let's look at the gassy formation. You're almost zero LPU values because the methane has very low density of hydrogen, so the LPU will be very small. In water, you have some value. What about in shale? In shale, because the neutron law recognizes it as it's all filled with water because the shell has also the hydrogen. So that's why you have a higher Q value, and higher Q value means that you have low density. 이해죠?